So how does the perceptron algorithm work? We start from setting all the theta equal to 0, and we check if with these parameters the classifiers make an error, and if it makes an error, we are going to correct the classifier, so updating its hyperparameters. And the update functions will be nothing else than the one given in this equation. So the new updated theta will be equal to the old theta when we add the product of the vector x for which he made an error with the associated label. So this can be -1 or +1, and we just sum the vector of the data making an error multiplied by its label to the old parameters, and this becomes the new parameter of my classifiers. Now, given what we said, the definition of error that we saw earlier, the first time when we have all theta equal to 0, are we gonna make an error or not? Can we tell is with certainty? Well, yes, because being this a vector of 0, the result will always be 0, so it will always be classified as an error. So the first data that the classifier will see will always lead to an update. So the first attempt will always lead to an error, and the first update will be theta 1 equal to a vector of zeros plus y1 that multiply the x vector of the first data in all the dimensions. Let's go to make a concrete example. So let's going to use 2 dimensions. We can visualize it easily. And let's say that our dataset is made of 2 points, x1, 2, and 4, so is this one, and the second is -6, 1, and both are negative labels. So our classifiers start with all 0, and we'll make an error, and when mapping x1, and the first update will become the old theta plus -1, that is the label of x1, that multiply 2 and 4, and will become the new theta will become -2 and -4. So here is -2 and -4 is here. So this is the norm of theta 1, and here is our first hyperplane when he saw only the first data. Now let's go and continue. We have x2 -6 and 1. Does this classifier make an error? Well, we can see here graphically that it make an error. Let's go to compute it. So let's go to have the label of theta 2 that multiply the current parameter of the classifiers with the dot product with the second point. So we have -1 that multiplied -2 -4 is the theta, -6 and 1 are the coordinate of the second point, and we can see here that the dot product is -2 that multiply -6 is equal to 12, plus -4 that multiply 1 is equal -4. So we have 12 -4, we have 8, and this is positive, so the dot product is positive, -1 is negative, so we have -8 totally, and we do have a classification error where the dot product doesn't match with the label. At this point, we run a second update, so the theta 2, the theta after the classifier made the second met the second point is equal to the theta 1 minus 2 minus 4 plus minus 1, the label of x2, multiplied by the feature of the coordinates of x2. So in total, the theta 2 will be 4 and minus 5, and is this one depicted here. And you can see here geometrically that at this point the classifier correctly classify both the points in this sample. More in general, we run the perceptron algorithm over the whole set of training data, starting from using parameter 0, the 0 vector, and then we'll go all through the training examples. And if the nth example is a mistake, at that point we perform the update that we discussed just earlier. So we moved the parameter in the right direction based, and this is the important point, of an individual update. However, since the different training example may update the parameter in different directions, the later update may also some sort of undo some of the earlier update. And at this point, because it's based on one individual parameter, or in one individual point, the update, some of the earlier example may no longer be correctly classified. So there are some cases, and it's the normal situation, where the perceptron algorithm needs to go over all the training set not one time, but multiple times in order to find a separable solution. And there is a theorem here that states that if the points are linearly separable, the perceptron algorithm, given enough time, will find a classifiers that do actually separate the points. So we have to go through the training set multiple times. And in the jargon of machine learning, this going through the training set to all the training set is called an epoch. This is not only the perceptron, but we'll see these terms in many different contexts. So we'll go through the whole algorithm. The function perceptron will be and something like this. We'll take our couple of data, the features and the labels, but we'll also take a parameter that we call it epochs, and we will initialize our theta to 0, and then for each of these epochs, we'll go through all the points and we'll check if the algorithm make an error, and if the algorithm make an error, we will update, and at the end we will return theta, or sometimes we will return theta and the number of errors. And typically, when we have many data, we will have many possible solutions, and the guarantee that we have with perceptron, with the theorem that I stated earlier, is that the perceptron we will find one, but not necessarily the best one. So here you can see here in 2 points, this could be a classifier's correct, this other one could also be correct. There are many classifiers, even if we limit to those passing through the origin, that would correctly classify this point. And in general, we will have many possible linear classifiers that correctly classify the points. And the perceptron will find one, not necessarily the best one. So here we move to something a little bit more advanced of the perceptron, but still somehow very similar. So